Good morning everyone, and welcome to today's worked exam answer question. Today we're having a look at an acids and bases question from an AQA A-level paper where we're covering a little bit on weak acids, and then on the back we're going to have a go at a buffer question, although they haven't used the word buffer in the question, so that is a new thing that AQA did for the first time in 2023. And then a little bit more on titrations at the bottom there. So the first part of this question, we're having a look at some different indicators. So when it comes to indicators that we're choosing for a particular titration, the pH range of the indicator, i.e. that would be the pH values between which this bromocresol green will change colour, that range needs to lie within the inflection of our titration curve. So we need to know for different combinations of weak and strong acids and bases what the pH range is for the inflection in the curve. So in this particular question, they are asking us which indicator would be most suitable for use in a titration between propanoic acid, which is a carboxylic acid, so it is a weak acid, and sodium hydroxide, which is a strong alkali or a strong base. So if we were starting with our propanoic acid, the initial pH would be about 3, and then that would increase slightly before the curve became vertical, and the vertical part is the inflection in the curve, and that is where equivalence has happened. We've added the right amount of moles of these two things together for them to neutralize one another, and that is when we then need the indicator to change color. And then because we're ending with sodium hydroxide, we would expect the pH at the end to be sort of 12-13 if we were to continue past equivalence and keep adding sodium hydroxide after that. So we first of all need to be able to identify that that is a weak acid and that is a strong alkali, and then we need to know that the inflection in the curve for such titrations is between a pH of 6 and 10. So we definitely cannot use bromocresol green here. I think there would be an argument for being able to use both of these because their pHs both, or their pH ranges, sorry, both lie between 6 and 10, which is where the inflection in the curve is, but it says identify the indicator that is most suitable. And based on the fact that bromothymol blue's lower end of pH range is bang on 6, I'm probably more tempted to use thymol blue because that sits wholly within 6 to 10 and doesn't include 6 or 10 in its range. So I'm going to go with thymol blue here as the most suitable. So you would need to know the inflections in the curve for a strong acid and a strong alkali, a weak acid and a strong alkali, a strong acid and a weak base, so a weak alkali, and then a weak acid and a weak base, which is going to ask us about in the final part of this question. Okay. The next thing we have to do is give the expression for the acid dissociation constant Ka for propanoic acid. So what some of you might find helpful is to first of all write an equation to show the dissociation of the propanoic acid. So CH3, CH2, COOH is acting as a weak acid, and we already know that because it says weak acid there. We know that because it's a carboxylic acid. We know that because we're being asked to write a Ka expression. That means that we're only going to get slight dissociation of the weak acid, so we're going to end up with an equilibrium mixture, so we need our reversible arrow, and once the Cu group has donated its proton, it will become COO minus, and then you'll get the proton like that, meaning for our Ka expression, it's going to be equal to the products over the reactants, so it's going to be CH3, CH2, COO minus in square brackets, times by concentration of H plus, and then the reactant is the weak acid, so concentration of the propanoic acid there. And that is our Ka expression. for the dissociation of propanoic acid. Now, we're about to work out a pH for the propanoic acid solution, and when we do that, we can simplify the Ka expression, because for every 1 molecule of propanoic acid that dissociates, we get both the negative ion and the H plus being formed in a 1-to-1 ratio, because you can't get anything else. You can't have a Cu group that leaves you with 2 COO minuses for every 1 H plus, because that wouldn't then be a Cu group. So that means that if we're making these in a 1-to-1 ratio, these concentrations will be the same. So when it comes to working out the pH of a weak acid, we can simplify the Ka expression so that on the top, rather than having these two different entities times by each other, if their concentration is going to be the same, we can simplify it to H plus squared. Now, please do not write this simplified version for your answer if you are ever asked to write a Ka expression. You should always write out the full version in a question like this. If you simplified it here, you wouldn't get the mark. So make sure you write it out in full, then simplify it when it comes to the calculation. The calculation is saying to us that we need to calculate the pH of a 0.1 mole per decimeter cubed propanoic acid solution. Got to give our answer to 2 decimal places, and we always should give our answer to 2 decimal places for pH, regardless of whether they tell us to or not. And then we've been given a sneaky pKa value here rather than a Ka value. So we need to know and be able to know the relationship between and convert between Ka and pKa, which works in the same way as H plus and pH. So in order to get pH is equal to minus log base 10 of the H plus concentration. So I need to rearrange this expression to get H plus equals. So to do that, I am first of all going to have H plus squared is equal to Ka times by the concentration of the weak acid. And then obviously I don't want H plus squared, I just want the concentration of H plus, so then I am going to square root Ka times by the concentration of the weak acid. So we've got the concentration of the weak acid there, it's 0.1. What we don't have yet is the value for Ka. Now, pKa is equal to minus log base 10 of Ka, so the same relationship as between pH and H plus. And if I therefore want to get the Ka, we need to do the inverse of the log, which is 10 to the power of, and then we're going to do the minus pKa. So Ka is equal to 10 to the power of minus pKa. And the log button and the 10 to the power of button are the same one. Mine is log for the main function, and then you'd press shift and log to get the 10 to the power of. So that's the first thing I'm going to do. I'm going to do 10 to the power of minus 4.87 so that I have my Ka value ready to go. And that gives me, to 3 significant figures, 1.35 times 10 to the minus 5. Then I can get my H plus concentration, because I'm going to do the square root of 1.35 times 10 to the minus 5 for Ka, times by the concentration of the weak acid that we were given as 0.1. And then once I've times them together, I'll square root whatever that comes out as. So square root my answer. That gives me a H plus concentration of 1.16 times 10 to the minus 3. And then that's my H plus concentration. So then I'm going to do minus log, and it has to be minus log. So the log button is just a normal log. So you've got to press the minus button first, then the log button, and then 1.16 times 10 to the minus 3. And that gives me a pH of 2.935, which if we're giving it to 2 decimal places would be 2.94. which is a pretty standard value for the pH of a weak acid. It's always been sort of, or they're always usually within that sort of realm, sort of the close to 3, could be 3 point something, or sort of 2.8, 2.9, that kind of thing for our weak acids. So hopefully that all makes sense so far, but as always, any questions, please leave them in the comments or send me an email. Turning over, this is where it gets complicated. This is a buffer question, but it isn't telling you it's a buffer question. So how on earth do I know that this is a buffer question? Well, first of all, we're using a weak acid again. We've changed the weak acid, but we still know it's a weak acid because A, it's a carboxylic acid, B, we've been given a Ka value. And we are going to add to 25 centimetres cubed of a 0.1 mole per decimetre cubed solution of that butanoic acid some sodium hydroxide, which is a strong alkali, as we already know from the first part of this question. Now, when we add a weak acid to a strong alkali, where the weak acid is in excess, which it is, as we'll see, and I'll show you how to see that in a second, we make the salt of the weak acid as one of the products, and whenever we have the weak acid and the salt of the weak acid in a solution at the same time, that will then act as a buffer. So, first thing that I need to do is write an equation for this reaction. So butanoic acid, CH3, CH2, CH2, COOH. That is going to react with the sodium hydroxide in a 1-to-1 ratio, thankfully, make it a little bit nicer. And the salt of the carboxylic acid is CH3, CH2, CH2, COONA. So not a hydrogen to make it an acid, but the sodium part from the sodium hydroxide will go there. And then we're going to make water. Because we're doing an acid and alkali reaction, we're going to get a salt plus water. And the next thing that I would do once I've written my equation is sort of use this as like a table. So we know the concentration and the volume of both the weak acid and the alkali. So that's going to enable us to work out the moles, and then we can figure out the excess moles. So concentration for the butanoic acid, 0.1. Also for the alkali is 0.1. The volumes we've been given in centimetres cubed, so I'm going to convert them into decimetres cubed. So volume of the weak acid is 25 centimetres cubed, so 0.0250 decimetres cubed, and 0.0200 decimetres cubed for the alkali. If I then work out the moles for both of those, the moles of the weak acid, 2.5 times 10 to the minus 3, and for the alkali is 2 times 10 to the minus 3. Now, because these react in a 1-to-1 ratio, the weak acid is in excess. I'm not going to be able to react all of this because I haven't got the same amount of alkali to react with it. I am going to be able to react away all the sodium hydroxide, and that's really important because you can't have any sodium hydroxide left over if you are trying to make a buffer. A buffer can only contain the salt of the weak acid and the weak acid itself, nothing else. Water's fine, that's just going to dilute the concentrations, but alkali definitely not. So all of this alkali, all the sodium hydroxide will react, and therefore we're going to have no alkali left, which is good. We're going to lose 2 times 10 to the minus 3 moles of the weak acid, which is going to give me 5 times 10 to the minus 4 moles left in excess. And then we can also work out how much salt is going to be made, because if the salt is then made in a 1-to-1 ratio with the weak acid and the alkali, we're going to make 2 times 10 to the minus 3 moles of the salt. We had none in the first place because it's a product of this reaction, so therefore we are left with 2 times 10 to the minus 3 moles of the salt that have been formed in this reaction that have created this buffer solution. Now, when we are calculating the pH of a buffer solution, we're going to come back to our Ka expression, which this time is for butanoic acid. So I'm going to write my Ka expression again. So we're going to have concentration of CH3, CH2, CH2, COO minus times by the concentration of H plus divided by the concentration of the butanoic acid. Now, when we were dealing just with a weak acid, we said that the negative ion and the H plus, they would be formed in the same quantity, because when one molecule of weak acid dissociates, we get one of each. We're not just dealing with a weak acid now, we've got the salt of the weak acid, and the salt of the weak acid is adding to the amount of this ion here that we have. So no longer can we say that these two things on the top are the same. What we can do, however, is when we rearrange this to get H plus equals, because we always want to get H plus equals whenever we're asked to get pH, we can use the moles rather than the concentrations. And that's something that I don't think is widely known or shared, but it makes things much easier because we've got the moles here. If we then wanted to convert those into concentrations, we'd have to add up the two volumes to get the new total volume, and then we'd have to do moles divided by that total volume to turn them into concentrations. Now, when I rearrange this, you'll see why that's not necessary. So because I'm going to use the moles, when I rearrange my Ka expression, I don't write the square brackets. But again, we have to have the initial version of the Ka expression written correctly with the square brackets, like this. So don't immediately drop your brackets when you're writing it this way. But if you're going to use the moles like I would suggest, then you can drop your brackets when you rearrange it. We can't drop the brackets on the H plus, that will still give us the concentration of H plus. But if we think about how we would be converting these moles into concentrations, we'd be dividing by the volume. So here we'd be doing the moles of the weak acid divided by 0.045 decimeters cubed. Here we'd be doing the moles of the salt divided by 0.045 decimeters cubed. Moles over a volume, which is equivalent to divided by, moles over the same volume. The volumes are going to cancel out, so we're going to be left with the moles. So whether you use moles or concentrations here and here, you'll get exactly the same answer. By using moles, you've saved yourself 2 additional calculation steps, which is hopefully going to just prevent any small errors from occurring, and save you some time, obviously. So now all I need to do is sub in my value for Ka, my moles of my weak acid, my moles of the salt, and that will give me my H plus, and then I can do minus log 10 of that value and I'll get my pH. So H plus concentration is equal to 1.51 times 10 to the minus 5 times the moles of the weak acid, 5 times 10 to the minus 4, divided by the moles of the salt, 2 times 10 to the minus 3. That gives me a concentration for H plus of 3.78 times 10 to the minus 6, and then minus log of that answer gave me to 2 decimal places 5.42. Now it doesn't say 2 decimal places here, they're going to expect it to be 2 decimal places. Okay, so I'm just going to very quickly highlight that that is the moles of the salt, that then goes there, because that is the moles of this. The alkali is not there anymore, so I don't need my purple. And for the weak acid, there, that is the moles of the weak acid, which is then going there. in my little equation. Okay, that may take a little bit of time to digest, and if you want to check it out, convert these moles into concentrations using the volumes, sub those values in, you should get exactly the same pH. Okay, and then finally, we're trying to titrate butanoic acid, which is still a weak acid, with a solution of ethyl amine. Now this is bringing in a little bit of organic knowledge here, because in the amines topic you learn that amines are weak bases, because the nitrogen of the NH2 group has a lone pair, it can accept a proton, that's what bases do. So here we have a weak acid and a weak base. Now again, the reason why we can't use a use an indicator in this titration links back to the pH range for the inflection in this type of curve, and there just isn't one. Starting with a weak acid, and then we get a tiny little vertical part, the inflection in the curve, and then we'll add more alkali, more weak base, and then, you know, the pH will gradually increase after that. So there is a very, very, very small, almost non-existent inflection in the curve, and there is not an indicator whose range fits solely within that inflection within the curve. So what am I going to include in this answer? I'm going to say that the titration is between a weak acid and a weak base, and therefore there will be no inflection in the curve within which there is an indicator whose range, that should really say pH range, for colour change I think that makes just about enough sense. So if we were to go back to the first question, and because we were looking at a weak acid and a weak base, we were looking at an inflection range of pH 6 to pH 10. With a weak acid, weak base, you would get a really tiny inflection in the curve. But if we have a look at these indicators, the pH range during which they change colour is fairly substantial. So we've got a 1.6 pH range there, 1.6, 1.6 again. And the inflection in the curve for a weak acid, weak base titration would not be as big as that. It would not cover 1.6 pH units, so therefore there will be no indicator whose pH range for the colour change falls within what little inflection in the curve there is. So hopefully that makes sense now I've explained it. Not sure I've worded that brilliantly, but the key thing is there's no inflection in the curve because it's a weak acid, weak base titration. Okay? Any queries about that, obviously let me know. Any queries about any of it, as always, let me know. And I hope that you found that beneficial. 100% suggest this method for buffer solutions, and if you have any other examples you want me to showcase, again, please just get in touch. Thanks so much for watching, guys.